How's it going, guys? My name is Ashton, and today this is Transport 2, Exam 2, and we'll be looking at a vertical column with wetted walls and liquid running down the side and a gas going up the middle. And what we want to do is characterize the system in order to reduce the number of dimensionless groups. And then we're going to be doing this via the dimensional analysis via the Buckingham Pi method. So what we first want to do is write out what variables we have. So first, our variables are going to be our mass transfer coefficient, our velocity, our density, our viscosity, our mass diffusivity, and then finally our diameter and their respective units, which are meters per second for our mass transfer coefficient, meters per second for our velocity. Our density is going to be kilograms over meters cubed. Our viscosity is kilograms meters per second. Our mass diffusivity is meters cubed, or meters squared, per second. And then our diameter is just going to be meters. And what we're going to do is put these into a dimensional matrix with our variables on top and our units on the side. So we're going to have our mass transfer coefficient, our velocity, our density, our viscosity, our mass diffusivity, and finally our diameter. And on the sides, we're going to have kilograms, meters, and then seconds. So first, we're going to be looking at their corresponding units and then the exponents with said units. So we know for the mass transfer coefficient, there's 0 because there's no kilograms. We're going to have a 1 because it's in the top, and then our seconds is the negative first power. And it's going to be the same for viscosity. Looking at our density, we're going to have 1 for the kilograms. We're going to have -1 for meters, and then another -1 for seconds. We're going to have 0 and then -3. And then for our viscosity, we're going to have 1 for the kilograms, a -1 for the meters, and a -1 for the seconds. And for our mass diffusivity, we're going to have 2 with 0 for the meters and -1 for the seconds. And finally, for our diameter, we're going to have 0, 1 for the meters, and then 0 for the seconds. And what we want to do is, and then next we're actually going to write out our the number of dimensionless groups that we want to characterize in the situation, which we're going to call I, and that is going to equal our n, which is the number of variables, minus our rank of our dimensional matrix. And in order to determine the rank of our dimensional matrix, we're going to be using Python, because it has built-in numerical Pythons we can use in order to determine the rank of our matrix. So I will be right back, and we're going to go code that out.
Hey guys, now I'm on the computer, and so currently we're going to be using Python in order to determine the rank of our matrices. So we're going to start off by we're going to import our numerical Python. So import numpy, we're going to call it np. We're going to shift enter that in order to import numerical Python. And now we're just going to create a variable in order to set our matrix to. So I'm just going to call my matrix matrix. I'm going to set that equal to np.array. And then what I did was I already made the array of data in a notepad, so I'm just going to copy and paste that in really quickly. But all you have to do is just type in each variable individually and just go through the rank of each one for each units. And then what we're going to do is we're going to use the linear algebra package in NumPy. So we're going to do np.linear algebra, and we're going to use the matrix and then the rank function in order to determine the rank of our matrix, which we call matri. And then if we hit Shift Enter again, it gives us that the rank of our dimensionless matrix is going to be 3. So now I'm going to meet you back on the whiteboard, and we continue on with everything we're doing.
Alright, welcome back, guys. I hope you just learned a little bit about coding with Python in order to find the rank of a matrix. And then from our Python code, we got that our rank, so our R is going to be 3. So then we're going to find the number of variables characterized, which is going to be 6, because we have 6 variables, minus our rank of 3 equals 3. So we're going to have a total of 3 total pi groups. So out of those 3 total pi groups, we're going to have 3 chord groups. And for our chord groups, we will be using our mass transfer coefficient because that has to be determined experimentally. And we will also be using, since we're using a mass transfer coefficient, we will also be using our velocity since it has the same units. And then that will just make the whole characterization easier due to cancellation. And then finally, we're going to be using our viscosity. So we can now, through these chord groups, we can write out each pi equation with our chord groups being in front, and then we can multiply those by the remaining variables raised to some exponential power, which we will determine. So first, we're going to have pi 1, which is going to be our Kc, and then we're going to multiply that by our mass diffusivity, so dAB, and then by our density, and finally by our diameter. Then we have pi 2, which is going to be our velocity multiplied by our mass diffusivity multiplied by our density times our diameter, and then finally pi 3, which is going to be our viscosity multiplied by our mass diffusivity multiplied by our density, and finally by our diameter. And we're going to raise all of these to a certain power, which we're going to find. So first, we're going to call this power A for mass diffusivity for the pi 1, B for our density on pi 1, and C for our diameter on pi 1. And then pi 2, we're just going to follow the alphabet and do the same thing. So D will be our mass diffusivity for pi 2. And then E is going to be our density for pi 2, F for our diameter, and then G for our mass diffusivity of pi 3, H for our density, and then I for our diameter. Now what we're going to do is we're first going to solve for these by knowing that we want them to be dimensionless groups. So we're going to look at the variables and then their corresponding units in order to determine their exponential powers. And then since we know they're going to be 0, we can set them equal to 0. So first we're going to be writing out our units. So meters transfer coefficient, we have meters per second. For our mass diffusivity, we have meters squared per second, raised to the power of A. Then we have our density, which would be kilograms over meters cubed, raised to the power C. And then finally, we have our diameter, which is just meters. Raised to the power B, which is raised to the power C. So then first, we can look at our mass, not meters. Then we can look at our kilograms, and then finally our seconds. So for our mass exponential coefficients, looking at our mass transfer coefficient, we have a 1 minus 2a minus 3b. I'm sorry, plus 2a since on the top, minus 3b since our meters on the bottom, and then plus c equals 0. Going to kilograms, we have 0 for our mass transfer coefficient, plus 0 for our a, since our mass diffusivity does not have any kilograms, plus b, because it's in the top portion, and then plus 0 equals 0. And then finally for our seconds, we have -1 minus a plus 0b plus 0c equals 0. And then solving for a really quickly, we get a is equal to -1, b is equal to 0, and then we can plug those that we just found into our first equation from meters. So we have 1 minus 2 plus 0 plus c equals 0, which gives us a c equals 1. So from there we can rewrite our pi1 equation. So we have pi1, which is going to be equal to our mass transfer coefficient raised to the first power. And then since our B0, our density is going to be initially a 1, so we can leave that out. And then we know our mass transfer coefficient, our A is -1, so we're going to write, or not mass transfer coefficient, I'm sorry, our mass diffusivity. And then we have our diameter, which is 1. And then if we look at pi2, since the units of velocity and our mass transfer coefficient are the same, we can correspond each variable that we determined in pi1 to the equivalent variable for pi2. So for example, our A is going to be the same as our D, our B is going to be the same as our E, and our C is going to be the same as our F. So this means that our pi2 equation is going to be our B times our D over our DAB, or velocity times our diameter over our mass diffusivity. And now looking at these are also commonly characterized, and they're found and used very commonly. So they already have certain names that correspond with them. So the first one we're going to have is our Sherwin number, which we can abbreviate as SH. And then the next one we can have our, it's called the Preslett number, which is going to be PE. And then since our viscosity is different, we can actually solve for pi3. And we can do this over here. We have some free space. So I'm going to flop sides real quickly. So for our pi3, we have, I'll rewrite it, we have our viscosity times our mass diffusivity raised to the power of G times our density raised to the power H times our diameter raised to the power I. And now we're going to do the same thing where we write out each of the corresponding units raised to their respective powers, and we're going to want to cancel those all out. So we're going to have kilograms over meters per second, or meters second, for our viscosity. Then, like before, we have meters squared per second for our mass diffusivity raised to the power of G. Then for our density, we have kilograms over meter cubed raised to the power H. And finally, we have our diameter, which is meters raised to the power I. Doing the same thing again, we have our meters, our kilograms, and then our seconds. So the first one, we have 1 plus 0g plus h plus 0 equals 0. Then for, oh, I'm sorry, I was looking at the wrong one. So we have actually -1. Let's just rewrite the entire thing. I'm sorry, I was thinking of kilograms. So for our meters, for our viscosity, we have -1. And then for our mass diffusivity, we have 2g. For our density, we have -3h. And for our diameter, we have plus I equals 0. For our kilograms, we have 1 for viscosity, we have 0 for G, we have 1, so H plus H for our density, and then 0 for I. And then for our seconds, we have -1 for our viscosity, minus G plus 0H plus 0 equals 0. So we get G equals -1. And with G equals -1, we can solve that H equals -1. So then with those two, we can solve for our I. So we have -1 minus 2G plus 3 plus I equals 0. So this means, and there's not a G there, it's just -2 equals 0, and then that equals -3 plus 3, which is 0, plus I equals 0, so I equals 0. So now we can finally write out our pi 3. So pi 3 is going to be equal to our viscosity over our density and then multiplied, and our density multiplied by our mass diffusivity. And then this is called our Schmidt number. And then looking at our relationship between some of these, we see that if we take pi 2 and pi 3, all the variables are there that make up the Reynolds number besides the mass diffusion or mass diffusivity. So if we take pi 2 and divide by pi 3, we get that velocity times diameter over mass diffusivity multiplied by the reciprocal of our pi 3, so our density times our mass diffusivity over our viscosity. Those cancel out to give us our velocity times our diameter times our density over our viscosity, which is also equal to the Reynolds number. So with that in mind, we can also write a relationship between the Sherman number, the Schmidt number, and the Reynolds number. And since naturally we know it's going to be exponential, we can have an idea that it's going to be our Sherman number equals some coefficient, call it A, times our Reynolds number, raised to the power B, times our Schmidt number, raised to the power C. And we will be using Python in order to determine those coefficients. So, thank you. I hope you learned something today, and I will see you back on Python.